All right, welcome to part 2 of Amplifier. That's what I'm going to call this series, and it's because I'm such a fan of the old Scott Paulson and Jim Crenshaw show that, well, some of you will know what I'm talking about, some of you won't. But anyway, enough of that. So we assembled this in the last video, and I kind of explained what I want to do with this series. I want to combine as many of your questions and comments as I can and integrate them into these video series to kind of show you, just give everybody a little bit of what they asked for. Of course, I can't answer everything that everybody wants to do, and I can't make a video about everything that you all requested, but I'll do my best here. So now that we have this together, what I want to do with this part of the video is I'm going to spend this episode explaining and reviewing how this thing works and what it is, kind of do some circuit analysis, and then let's compare it to a couple of the old Pioneer amplifiers that are you're going to see a lot of similarities to the design of this amplifier versus those ones, but you can see how the commercially built ones are more refined than this. And then what I want to do in the next series is, in the next episode, is I want to actually test this amplifier. If it works, we'll have to turn it on and see if it works. If not, we'll troubleshoot it. We'll get it to work. And then compare it to the quote-unquote more refined versions of this amp. And hopefully by the time we're done with this series, we'll all have a much better understanding of how transistors work, how the different circuit parts work individually, and how they all work together, and how an amplifier works. Okay, but really this is a good general electronics exercise, I think. So let's get started. So here's the only page that comes with this kit, and of course I can't read that, but thanks to the modern technology of Google Translate, I was able to take a picture of that, translate it, and print it out. So what it basically says is this is a typical OCL circuit. So what is OCL? Well, it's not the same as OCD, thankfully. That means output capacitorless. What does that mean? Well, that means that this isn't one of those amplifier designs where you have a DC blocking capacitor between the output, of your big output transistors and your speaker, which means that the junction point of these two transistors is sitting at 0 volts. There's no DC offset to it. We'll look at that a little bit more here, and we'll look at some examples later on here. And do you remember in the last video I said just by looking at this schematic that this thing's probably not going to put out more than, it's going to be anywhere from 8 to 15 watts. Well, they're kind of calling it a 20 watt output into 8 ohms and 30 watts into 4 ohms, and that's even going to be pushing it to the maximum. Remember, these heat sinks are kind of small. If we wanted to move these off of the board and relocate them onto a big heat sink, we could increase the power capability of this by a little bit. But remember, these caps here are only rated at 35 volts. So you really don't want your DC rail going much more than 25 or 30 volts. You want to have a little margin of error with these caps. So just by the very nature, you're never going to get that. Now how was I able to figure that out? All right, let's do our first little analysis thing. Now if you look at the recommendations on this, and I'll zoom in, they're saying that primary voltage of AC 220, in our case 120 volts, and if you're in Europe 240 volts, that doesn't matter. But the secondary, they want 2 sets of AC 12 to 18 volts. So they're saying the sweet spot for this amplifier is if you have a dual 12 volt or dual 18 volt, or sometimes they refer to it as an 18-0-18 or 12-0-12 transformer. It's just a transformer with a center tap. So let's go to the best case scenario. So taking into account that, let's say we're going to use the best case scenario, your 18 volts. So if you take 18 volts AC RMS, the DC voltage of that, when you full wave rectify it, is going to be 1.414 times that. So let's times that by 1.414. And you could see you have about 25 volts DC. Now, there's some caveats to that. Depending on your transformer, depending on the capacitors you're using, and depending on the actual wires and everything, you're going to have some sag in that. So if it's 25 volts with no load on it, when you put a full load on it, it's going to be back down towards that 18 volts, somewhere around 20 volts, let's say. So let's say realistically, we have a maximum of 20 volts DC. All right. So we have 20 volts DC to work with. And we're talking plus and minus 20 volts, because you're only going to move 20 volts in one direction at one time. In other words, you're never going to see the full 40 volts, between the plus and minus. It'll go from 0 to plus 20, then it'll go back to 0, and then it'll go from 0 to minus 20, and then back to 0 if we're doing a sine wave, right? And the RMS is going to be not peak to peak, but the peak voltage times 0.707. So anyway, 20 volts. Just follow me on that. If we take 20 volts and we square it, and we divide that by an 8 ohm speaker load, that means you can technically get 50 watts. So you say, well, why are they saying it's only a 20 watt amp? Shouldn't this put out 50 watts? No, not how it works at all. This is a Class AB type amplifier. And while it is a little bit more efficient than a Class A, it is still not 100% efficient. This is not a Class D amplifier. So whatever power you have there, you can figure that you're only going to have about 70% at the very most, usually closer to 50 to 60%. So let's say generously 60%. So we have 50 watts times 0.6, you're closer to 30 watts. And you can see that's kind of where they're putting this. Into 4 ohms, you can get a 30 watt dissipation, and into 8 ohms, 20 watts, because that's just the amount of current that this thing's going to be able to supply at that voltage. See how that is? So a lot of times, when we look at that other one that's listed on there right now on the internet, it's the same amplifier. Remember, they're putting a little bit more power in it, but they're saying 80 watts. Well, that's kind of being pretty generous. 80 plus 80. That's really not what you're going to see. So just remember, looking at the power supply and so forth, you can get a really good, the power supply and circuit design, you can get a really good idea of how much power the amp is expected to put out. And of course, when you finally look at this, they pretty much tell you. So they're being pretty honest here. So let's start by doing a little bit of review. I went on to MS Paint and I just drew out this little outline diagram. This is a block diagram of your typical amplifier. And actually it is pretty much what this is. And we'll go back and forth and look at those sections here in a second. So you can break an amplifier down, at least the types that we're talking about, into 4 sections. And you can see some things are optional and some things aren't, but you have your input / negative feedback section. That's over here. I'm going to move this out so the color doesn't get weird. Then that drives your voltage amp stage, or your VAS. So whenever you hear people saying the word VAS, V-A-S, they're talking about the voltage amplification stage, and that's what this is. And in some cases, depending on what kind of output you're going to have, what this circuit design is going to be, you may also have a phase splitter or phase inverter transistor and some pre-drivers, a couple transistors after you split the phase that amplify the voltage a wee little bit more. That's all going to be what I'm going to call this section, okay? And when I troubleshoot an amplifier, this is how I break them down. Remember, these are all direct coupled. There's no capacitor in between them. There's a direct line connecting them. And that's why if you short one thing out, it puts a short circuit on everything behind it. And that's one of the problems with direct coupled amps. Now from there, it drives your output. And your output section can also have options. It can be a single-ended output, meaning it could be as simple as one big transistor that is biased halfway turned on in its midpoint, and then it can go up to its maximum and down to its minimum, and that's where you're getting your sine wave, and that's usually just uses a single power supply. You can have a single-ended push-pull, or better known as SEP. It's technically a single-ended amplifier, but there's two transistors and there's a midpoint, and it can go up and down. And that midpoint can either have an offset voltage or 0 volts, depending on if it's a dual power supply or a single power supply. And as you can see, this negative power supply is optional. Some amps are a single rail. They'll have a plus VCC and ground, and the midpoint will be sitting at some voltage in between there. It can also be a complementary amplifier, and you'll have a negative voltage and a positive voltage, and they'll be equal and opposite, and at the center point where they meet together, they cancel out and equals 0 volts. So when you when you turn one of them off or on a little more, the other turns off more, the voltage at the midpoint will either go up or go down, depending on which side you turn on or turn off. And then you have a true complementary push-pull, which those will use this phase inverter and all that. And they're just a little different design than this, the way they're driven, the way they're biased, and so forth. Now, from your output section, to reduce distortion, you come out of the output where your speaker would be, and they loop it back and connect it back into your input, and that's called negative feedback. And what it's going to do is it's going to be a signal that's going to be opposite polarity of what your input signal is. So it will oppose the input signal. Why would you do that, you say? Well, that's for reducing distortion, and that's another whole video in and of itself. Now, that negative feedback can be done in a couple different ways. You can have your differential input pair, which is going to be, this section here where you see these two little transistors. That's called a long tail pair. This is called the tail resistor. This is your current source here. It can be active or passive. This one's passive. It uses a resistor. Or you can have just something as simple as a Class A amplifier or transistor, just a single transistor, and at the output of the transistor you're feeding this in there, okay, and it will actually provide negative feedback to that section. There's a lot of bad things to that too. It's not perfect. It is much better to do it this way. The other way they could do it is you can have an actual integrated circuit op amp, and you can get your feedback through that. An op amp has a similar circuit to this inside of it, but it has a lot of other things to make the signal a lot cleaner. So again, they're all doing the same thing. You're just taking that input signal, you're applying an input impedance to it, and then you're outputting. Sometimes they'll have gain, sometimes this won't have gain in it, or it'll have just a little bit of gain. It may have a lot of gain, and they may skip this section altogether. If it's a really tiny amplifier, you'll have this, and it'll directly drive the single-ended output. Just depends. Again, it has to do with the design. And then, of course, your feedback circuit. Your voltage amp stage is usually reserved for amplifiers that have a little higher output power. Something that's not in the milliwatts, or something like a transistor radio. You'll have a voltage amplification stage, and its whole purpose is to increase the amplitude, the voltage amplitude of the signal that's coming in here. Because it's very tiny in here. Usually the signal coming in here is less than 1 volt RMS. And you need 20 volts RMS, let's say, to get an output to the speaker. If you wanted a like 50 watt amp or something. And so you have to increase the voltage. So that's what this does. This gets the amplitude. But the problem is I can amplify that voltage, but I'm using this tiny little transistor, like these ones here. And if I hook a load, like a low impedance load, like an 8 ohm speaker, at that kind of voltage, that speaker is going to want to draw a lot of current. And these little transistors can't deliver that much current without burning up. So what you have to do is, that's what the output section does. It does not amplify the voltage, but it does amplify the current. So what this does is the voltage coming out of this is the same as the voltage coming across here most of the time. Some outputs do have a little bit of extra gain, but a lot of them do not. But what this will do is this will convert that high impedance signal to a low impedance signal. So it'll have the same voltage amplitude, but it will have a lot higher current capability. So when you have a low impedance on there, like 8 ohms, 4 ohms, 1 ohm, it can drive it. Now last of all is this fourth part, which is called the protect circuitry. And it's all optional. Some amplifiers, like this, has absolutely no protection circuit whatsoever, none. And you can have offset detection, so you never want any DC voltage going into your speaker. That will fry your speaker on very short order, and anything like, even like 1 or 2 volts can really trash a speaker if you put DC voltage on it. So you can have a circuit in there that will monitor that speaker terminal. If it ever sees a DC voltage above a certain threshold, there's a relay that will disconnect the speaker from the amplifier. Now, it won't protect this from burning itself up. It will protect your speaker from getting burned up by this that's not working right. You can have overvoltage and overcurrent protection. So there's circuitry that will monitor the current going out to the speaker. And if the current exceeds the current limit of these transistors, it can actually shut down the transistors. It can prevent the drive signal to the transistors from driving them that hard. It'll back it off so that it limits the amount of current. You can also have an overvoltage protection circuit in here that if you overdrive that input of this, it won't overdrive your output. At this stage, that overvoltage circuit will actually clamp off that signal here and attenuate it so that you never get too much drive into this. And last but not least, you have an actual power limiter circuit, and that actually looks at the actual power in watts that your speaker is dissipating, regardless of the current and the voltage. It's looking at the overall power being dissipated by that speaker. If it exceeds a certain amount, then it's going to throttle the amplifier back so that it can't drive it that hard. It won't let it drive beyond its limit that it's set to. So those are all options, and the higher end amplifiers will have 1 or more of these, and the lower end ones will not. So that's in a nutshell how an amp works. Now, as you can see, like a complementary amp can have a positive and negative voltage driving them, and these are unregulated. You have a transformer that goes through a bridge rectifier, 2 big capacitors, and then into here. Not very well regulated. And in the lower cost amps, such as this one we're going to see, they just pick off a voltage and go through a resistor, put another capacitor on it, and they feed the input signal from that. On higher end amplifiers, they'll use a very regulated power supply, very low noise, because this is the sensitive part of the amplifier. This can amplify very small signals, even very small noise signals. So if you have some power supply noise, that'll affect it. In addition, when you're driving a heavy load, this power supply is going to sag. It's not going to stay. Remember we said earlier, when there's no load on it, we have 25 volts, but when you put a load, it'll drop down to 20. That's fluctuating up and down. So this input amplifier is fluctuating up and down, and that little bit of voltage change might make a big difference on this, and it can cause distortion. So that's why a lot of the higher end amps, they'll use a regulated supply. This is not high current, but it is highly regulated. And you see it can drive either just this or this and this section. So there it is. That's, in a nutshell, how an amp works.